Hi, I'm Akshay. This is the video for our SIGCOMM 2024 paper titled Principles for Internet Congestion Management. Let me start with the state of the world in congestion control today. So the norms and community enforcement that we had in the past that governed how we would adopt congestion control proposals and protocols have now given way to more of a wild west of congestion control algorithms and mechanisms. So as an example, let's consider a few recent congestion control mechanisms which originated in industry. So industry practitioners designed these algorithms to optimize the throughput and latency that their applications experienced. And of course, what came after was the backlash from researchers who analyzed these new algorithms, and especially in the most well-known and well-studied case of BBR, found that the algorithms didn't compete fairly for throughput with existing commonly deployed congestion control mechanisms like Cubic and Reno. And it's important to acknowledge with BBR that the authors have responded to these concerns with changes to their algorithm. So we're now on BBR v3. But the real point is that the internet is clearly no longer in this sort of regime where concerns with TCP fairness can reasonably prevent a CCA's deployment, right? We're past that. Clearly, BBR was deployed without this being an obstacle to its deployment. So if TCP fairness is no longer relevant, what mechanism should we be using to allocate bandwidth in the internet? So the goal that we propose in our work for this mechanism is what we call CCAI, or Congestion Control Algorithm Independence. What we mean by this is that the throughput a given internet stream can expect shouldn't depend on the interactions the chosen CCA has with other traffic's CCAs. So one thing to discuss here is what impact providing CCAI might have on the design of these congestion control algorithms. So currently we can think of a CCA's job as comprising three things. So first is discovering the available bandwidth and using it to the greatest extent possible. Second is minimizing the queuing delay that the traffic that you're controlling experiences. And third is doing this relative bandwidth allocation task of sharing bandwidth fairly with other flows. And this bandwidth sharing task has been shown in prior work to be quite difficult as a CCA design property. With CCAI, algorithms wouldn't have to worry about fairness anymore since bandwidth allocation could be handled by some external mechanism that we're going to talk about later in the talk. And as a result, embracing CCAI in the internet would recognize this explosion of interest in new CCA designs that we've seen in recent years and allow users to design CCAs to focus on the core trade-offs in CCA design that we've seen people optimizing for over the past, say, half decade. That is trading off throughput, latency, and sensitivity to changes in available bandwidth. That's what we really want our CCA designers to be thinking about. Probably the simplest path to CCAI would be to use a traditional idea, which is isolation between flows implemented with a mechanism such as fair queuing. So instead of treating our queue as a single queue, like in the top half, if we instead divide the link's bandwidth between multiple virtual queues with one virtual queue per flow, then the CCA the flows use doesn't affect their bandwidth allocation as long as they have at least one packet in the queue or their virtual queue. So are we done now? If we want the internet to provide CCAI, should we just advocate for the universal deployment of fair queuing? Unfortunately, while that solution works technically, it doesn't work economically. And we've actually known this for a long time. This is because the internet is an economic system as well as a technical one. So Bob Briscoe famously observed this in his 2007 CCR paper, in which he pointed out that flows actually have nothing to do with internet economics. They're not economic actors. What we mean by this is that flows as a concept are unrelated to the economic arrangements that actually make the internet work. So if we were to advocate for a universal deployment of fair queuing, that isn't something that we should expect to happen naturally, right? There's this impedance mismatch of economic incentives that works against it. So we need another solution if we want something that's going to be practical for the internet. So to come up with a solution that does fit the internet's economics and is thus something that we could reasonably advocate for deploying, we should understand first what the economic properties of the internet are, right? So there are two primary properties that are most relevant in our case. The first is the pay for access model, in which we pay money to a provider in exchange for access to that provider's negotiated internet routes. The second is the recursive structure of these access agreements. So your provider will in turn have an economic agreement with some other provider or some other domain that eventually provides you with access to the part of the internet that you paid for. So the key idea in this paper is to take the economic properties that we just discussed and use them as principles for internet bandwidth allocation. So if we allocate bandwidth to traffic according to these principles, rather than using the old framework of TCP fairness, then we'll have achieved our goal of CCAI, congestion control algorithm independence, while still remaining consistent with the internet's economic properties. So the first principle that I'd like to develop is relative rights. So if two customers of the same provider have different economic agreements with that provider, in cases of congestion, the provider should allocate more of the bandwidth to the customer that pays more. So we can consider this principle in terms of when there is a congestion event and we have to drop packets, we should drop packets corresponding to the economic agreements that we have. This principle draws from the differential access that we can already see today, where if all senders blasted traffic, they would still achieve different throughputs today due to a combination of access limitations and arbitrary router decisions to drop packets. The main difference that we propose is that this differential access should not only be at the edge, for example, enforced by access speed restrictions, but also throughout the internet in various parts, in various domains. So the second principle that I'd like to discuss relates to the recursive structure of the internet's economic agreements that we saw before. Remember that under principle one, provider A here only enforces relative rights if there's congestion in provider A's network. If the congestion is elsewhere, somewhere downstream, principle two states that a packet's relative rights should accompany it through the network. So to see what I mean, let's consider this case. So provider A isn't experiencing congestion, but provider B is. And when provider B drops packets, it has to choose between provider A's traffic in aggregate and customer three's traffic. Under principle two, we're saying that it should additionally consider which portion of provider A's traffic to drop, right? Customer one or customer two's traffic, depending on those two customers' relationships with provider A. Finally, we need to handle cases where there are no relevant economic agreements, right? There are parts of the internet where the internet isn't acting, has no economic properties. So we need to figure out how to allocate bandwidth in these cases. So for example, in this slide, customer one is running both application one and application two, and we need a way of deciding which application's traffic will get dropped when there is congestion. So our answer is principle three, that there is no possible internet-wide answer to this question that can be universal. And as a result, we should leave the answer to individual endpoint domains, which can decide the relative value that they derive from the traffic of various applications that they run. I don't have time in this talk, unfortunately, to discuss how the customer might answer this question or what policies they might use, but I'll refer you to the paper for a discussion of the possibilities here. So putting these principles together, we derive a bandwidth allocation framework that we call RCS, or Recursive Congestion Shares. The three principles combine into a mechanism that looks like hierarchical weighted fair queuing, or HWFQ, which is a traditional idea in networking, but with guidelines on how to set the weights. So since we based it on economically derived principles, RCS as a framework is something that we argue is economically consistent with the internet as it exists today. So now we can ask the question, does this bandwidth allocation framework actually achieve the CCAI goal that we set out to achieve? And interestingly, the answer to this question in the most general case is that no, it actually doesn't achieve CCAI in all possible cases. Throughout the process of our work, we've generated counterexamples with things like cyclical interactions between traffic, in which following RCS in those examples doesn't actually provide CCAI. And there are more details about these tough counterexamples in the paper. Instead of asking about all possible topologies, we can determine whether the CCAI property holds for many or most topologies, especially those topologies that are structured similarly to the internet topology that we can actually observe today, which is the ones that we should probably care the most about, as well as randomly structured topologies so that we can cover any future topological evolutions. So the way that we're going to determine this is using game theoretic analysis, where the topology and weights are the game, and then individual traffic sources are the players in the game. The details are in the paper, but the high-level question that we're going to ask is whether there exist player strategies, and these strategies are sort of analogous to aggressive CCAs in our case, that enable the player to manipulate the outcome of the game in their favor so that they get a favorable bandwidth allocation. So this slide shows one aspect of that analysis. So without getting too deep into the game theory, and for details on that, I'll refer you to the paper, we can classify topologies as providing CCAI or not. So in the overwhelming majority of cases that we evaluated, including both the random topologies that I mentioned, as well as those we constrained to have a structure that's similar to the graph structure evident in KIDA's AS relationships dataset, RCS provides CCAI in this vast majority of cases. For these KIDA sample topologies, in fact, we couldn't find a single case where RCS didn't provide CCAI. For random topologies, we did find some cases, about 5%, in which there was a theoretical lack of CCAI. So when we dug deeper and investigated these cases more closely, we found that the average gain in throughput that an aggressive CCA would be able to achieve on these pathological topologies was about 0.01%. So in other words, in almost all cases, and in every case that is representative of the graph structure of the internet that we have, RCS provides CCAI. And even in cases on pathological topologies where CCAI is violated, the gain that an aggressive CCA could achieve is extremely small. It's 0.01%. So we've shown that for most topologies, the expected gain from using an aggressive CCA in RCS probably wouldn't merit the effort of developing such an aggressive CCA. You would just use a normal CCA and play by the rules of the game. So next we can move from theoretical results to practical results. How will real CCAs that we have today behave if we use RCS? And do the same findings apply? And here we use emulation-based experiments to find that, yes, actually, RCS still holds with real CCAs today using emulation experiments. So first, when we implement each of these mechanisms in our emulated topology, so we sample another 10 topologies from the KIDA dataset for this experiment, and then for each of those topologies, we run 10 experiments where each flow gets a random CCA assignment. So we can ask whether the allocation a flow gets remains stable within that topology across these various random assignments of CCAs. If the allocation isn't stable, we know that we haven't provided CCAI, since the random variation in CCA assignment across iteration clearly caused a difference in the bandwidth allocation that that flow got. So we find in this graph that, as expected, using traditional FIFO scheduling doesn't provide CCAI. But using fair queuing as well as RCS's hierarchical weighted fair queuing approach do provide CCAI, and we can see this because the spread in bandwidth allocations across CCA assignments is very low for both of those configurations. The second question that we can ask, given that we know that the allocations were stable from the left graph, is whether the allocations match the ones that we actually predicted using our game theoretic analysis. So in other words, are the allocations consistent with RCS, and therefore are they consistent with our modeling of the internet's economics? And the biggest difference is, of course, that while fair queuing was able to offer CCAI, its allocations differ quite a bit from what the economic principles we derived indicate that they should have been. So there are a few other important issues with RCS that I haven't been able to discuss in this talk. The first is practical concerns around implementing, deploying, and scaling RCS. I'm not going to talk about these much in the talk and will instead refer you to the paper for a discussion. But the high level takeaway is that we believe that there aren't major technical hurdles to deploying or implementing RCS. A second important aspect of RCS is the fact that it establishes an explicit relationship between bandwidth allocation and economic arrangements in the internet. So it's reasonable to ask whether this bandwidth allocation mechanism is an equitable one and whether it conforms to expectations about net neutrality. So we discussed this in the paper, but we believe that RCS is compatible with generally accepted notions and definitions of net neutrality, especially considering the economic structure of the internet today. Finally, I'll briefly discuss RCS's deployment prospects. So we acknowledge that we're proposing a big change in the internet architecture, and we're realistic about its chances for deployment being low in the near term. But one of the benefits of RCS is that it offers a way for domains to sell a tangible product to their neighboring domains in this relative rights product, which, if you sell it, offers a specific service that downstream domains can then resell to their neighbors and so on. As a result, and we show this with experiments in the paper, even if only a few domains along a path deploy RCS, they can significantly increase the level of CCAI on the path. That is, the effect that changing your CCA to an aggressive one would have on that path would decrease significantly. So given the ability to sell this service as well as the incremental benefits of RCS's deployment, we think that RCS is a practical proposal that could be adopted in the medium term for the internet. Thanks so much for listening to this talk. If you'd like to know more, I'd encourage you to read the paper for all the details, as well as contact me or any of the authors via either email or in person at the conference. Thanks.